Welcome back to Integral Calculus. In this video, I want to talk about improper integrals. An improper integral is an integral that is flirting with infinity. There are a couple of different ways that we can think about them. The most straightforward is probably something like the integral from 1 to infinity of dx over x squared. Right? We say that this is an improper integral because according to mathematics, you can't put infinity as a limit of integration. That's nonsense. According to physics, engineering, and honestly even statistics, which is some people still think is part of math, even though I don't, they just do this all the time and don't worry about it. But technically, this is wrong. The correct way of approaching this integral is to write it as the limit as b goes to infinity of the integral from 1 to b of dx over x squared. This is a much better way of doing it because now we can evaluate the integral the same way we always evaluate integrals. And in this case, it's a relatively simple integral using the power rule. So negative 2 plus 1 is negative 1. So we'll have 1 over negative 1 times x to the negative 1, evaluated at 1 and evaluated at b. Well, as b goes to infinity, negative 1 over b is going to go to 0, and we're going to be left with 1. That's it. Now, if I were teaching a physics class instead of teaching a math class, I would not have bothered with writing anything involving a limit. I would have just said, oh, this is negative 1 over x evaluated at 1 and infinity. That's negative 1 over infinity minus negative 1 over 1. Oh, that's 0 plus 1, which is 1. But this is not physics class, this is math class. And in math class, this is wrong. If you are studying math, make sure that you understand this process. If you are studying physics or engineering and you want to be lazy, 50-50 whether you can get away with the other one. This is where my background as a physicist is probably a hindrance to my ability to teach math. I have been told more than once I teach math like a physicist and I teach physics like a mathematician, which is probably the worst of both worlds. But it is the things that make sense to me, and one of the things that makes sense to me is, why are we writing all of this out? Well, we're writing all of this out because writing 1 over infinity is nonsense. That's not something we can write. In mathematics, there is no mathematical definition of it. But I also want to be a pragmatist. I want to be pragmatic about this. And really, most of the point of mathematical notation is so that we can be lazy and write less. So when I write an infinity, I am really talking about a limit as something goes to infinity, and I'm just being lazy and not writing it out. Understanding that and being fluent with that is something that will be valuable for you if you're moving onward in the study of physics, engineering, and probably chemistry. If you're moving on in the study of mathematics, that's probably not going to be very valuable to you. So take out of this what you think is the most useful. A very similar looking expression, the integral from 1 to infinity of dx over x this time, has a surprisingly different result. Because the integral of 1 over x is the natural log of x. Well, natural log of 1 is 0, so we just end up with natural log of b here. But unfortunately, natural log of b does not exist. It tends towards infinity. That is absolutely something that can and will happen. When it does, we say that the integral diverges. Right, so slightly different language than what we use for limits. We're going to use that same idea of when there is a result, like there was in the last problem, it would be more technically correct to say that the integral converges to 1. And when the limit does not exist, it is technically correct to say that the integral diverges. I'm not going to be a huge stickler about the vocabulary, but this is math, and if I'm not showing you the vocabulary, are we really doing math? So here's a messier one. The integral from negative infinity to infinity of e to the x dx over 1 plus e to the 2x. We have positive infinity and we have negative infinity. And when I was a student, I really wanted to shortcut this, but shortcuts actually can cause problems. I don't know if they do in this particular one or not, but there are some integrals that have limits of integration at positive and negative infinity that are problematic. So we have to write this as two separate limits. The limit as b goes to infinity of the limit as a goes to negative infinity of the integral from a to b of e to the x over 1 plus e to the 2x. In order to evaluate this limit, I'm going to do a use substitution. I don't like that there's exponentials going on here, so my immediate thought is, well, what if we let u equal e to the x? Then du would be e to the x dx, and our limits are still the same. Our limits of integration are still the same, because as a goes to infinity, e to the x is going to go to infinity. Although I guess as x goes to negative infinity, e to the x doesn't go to negative infinity. E to the x is only going to go to 0. So that's something a little bit different. We actually don't need that second limit anymore because it does work, but it's probably safer to keep it. Integral du over 1 plus u squared, that's just arctangent of u and of course u is e to the x. Right? We could deal with the, right, it's actually 1 over a times arctangent of u over a, but a is just 1, so we can be lazy and not have to write all that stuff out. All right, so we end up with arctangent of e to the b minus arctangent of e to the a. And if we take the limit as a goes to negative infinity, well, we'll have e to the negative infinity, which is 0, and then the arctangent of 0 is 0. Then we have the limit as b goes to infinity of the arctangent of e to the b. As b goes to infinity, e to the b is also going to go to infinity. But then think about what arctangent looks like. Right? Arctangent is tangent turned on its side. And has horizontal asymptotes at negative pi over 2 and positive pi over 2. So the one at positive pi over 2 is the one we're going to be approaching. And in fact, this integral converges. It converges to pi over 2. That's somewhat strange, I guess. Have to really think about our transcendental functions in order to get through that one, but we were able to. I've got one more example that I want to go through in this video. And that is the integral from negative 1 to positive 2 of dx over x cubed. This doesn't look anything like the examples that we've dealt with so far. The limits of integration are both finite. I'm not writing infinity here anywhere, trying to disguise the fact that there is a limit. In fact, what I'm doing is worse. I'm disguising the fact that there's an infinity. My integrand is f of x equals 1 over x cubed. And 1 over x cubed has an asymptotic discontinuity at x equals 0. Right? The graph looks something like that. So it's not the limits of integration that are flirting with infinity, it's the function itself that is flirting with infinity. So we cannot evaluate the function when x is equal to 0, and 0 is right in between those limits of integration. So we're going to rewrite this as the limit as b goes to 0 of the integral from negative 1 to b of dx over x cubed. plus the limit as a goes to 0 of the integral from a to 2 of dx over x cubed. By doing it that way, right, basically the upper limit here and the lower limit the second time are both 0. And we've seen many times in the past that we can split an integral up over its limits of integration by just matching the upper limit on one to the lower limit on the next. And this is covering the same integral, but now we check in both cases and make sure that we don't accidentally go to infinity. Accidentally going to infinity is just as bad as intentionally going to infinity, except you might not notice that you did it, and you might not notice that anything has gone wrong. All right, so integral of 1 over x cubed. That's going to be negative 1/2 times x to the negative 2. And when I try evaluating this, see, that's going to be negative 1/8, and then it'll be plus 1 over 2a squared. And unfortunately, as b goes to infinity, that's going to go to, I'm sorry, as b goes to 0, that's going to go to infinity. As a goes to 0, that's going to go to infinity. And so we've got infinity plus 1/2, and we've got negative 1/8 plus infinity. Either case, these limits do not exist. So the integral diverges. I think that sort of reasoning is incredibly important. So I want you to try one similar to that. The integral from 1 to 3 of dx over x minus 2. Right. This is the problem at the end of the video on improper integrals. So it's not a surprise to you that this is an improper integral. But I want you to go through this and make sure that you're paying attention and you can recognize why this is an improper integral, so that if you come across something like this in the wild, outside of this particular lesson, you know what you're doing, you know what you're watching for. All right, take a few minutes to see what you can do there, and I'll see you in the next video.